This is the 14th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. In this video, we'll look at ways of measuring the size of combinatorial circuits. Measuring size is more straightforward than measuring time because we can just count the gates. We don't have to worry about what's in parallel and what's not and so on. But again, just as when you're measuring time, if what you're trying to do is check out the growth of a family of circuits as you add inputs, you have to remember that n input gates are bigger than 2 input gates. Okay, so once again, let's use that same model where we assume that all the gates are 2 input gates, so that anytime we want an n input gate, we just build it out of a tree of 2 input gates, and let's see how the size grows. All right, so let's look at the pattern. We'll again start with a single 2 input gate, which of course has a size of 1. And then if we add a second level to the tree, we can get 4 inputs, but that takes 3 gates. If we add a third level, we can have 8 inputs and we get 7 gates, and so on. So pause the video and see if you can figure out the pattern. All right, so it turns out that a tree with n inputs uses n-1 gates, which means an n input gate has a size that's big O of n. Now I'll let the pattern speak for itself in this video, but your discrete structures class, which is Math 325 here at Grand Valley, will cover trees more thoroughly, including where this formula comes from. So if we count n input gates as big O of n, what's the size of the ripple carry adder? Well, first we need to know the size of the component full adders. In this case, we would say that this full adder requires 7 2-input gates, assuming we build the 3-input gate out of 2 2-input gates like this. Now, overall, we call this big O of 1 because the number of gates needed is constant. It doesn't depend on the number of bits in the ripple carry adder's input. This full adder is the same regardless of whether it's part of a 4-bit adder or a 400-bit adder. That means that this 8-bit ripple carry adder uses 56 2-input gates, and the general ripple carry adder design has a size that grows linearly with the number of inputs. Finally, let's look at the size of a circuit built using the brute force design. Pause the video and see what you come up with. All right, so as before, the NOT gates are just single gates, but we have to count all n of them, so they contribute big O of n. Each AND gate here also contributes big O of n because it has n inputs, but there could be 2 to the n of them, 1 for each row in the truth table. So this block of AND gates has a total size as big as big O of n 2 to the n. And finally, the OR gate, for the same reason, can have 2 to the n inputs, so its size is big O of 2 to the n. So when you combine these all together, you get a total big O of n 2 to the n. So with this kind of growth rate, it's easy to see why this technique is only practical for relatively small circuits. All right, let's summarize. When measuring the size of a circuit, you can simply count all the gates. We don't have to look for critical paths or anything like that as we do when looking at the time of a circuit. If you're trying to describe how the size of a family of circuits grows as you add inputs, remember that n input gates are bigger than 2 input gates. So one way to account for this is to assume that the n input gates are trees of 2 input gates. These trees will have a size that's linear. When using this approach, the family of ripple carry adders grows linearly, but a family of circuits designed using the big hammer grows exponentially. And remember, using the big O and the trees of gates and all that only applies if you're looking at the growth of a family of circuits. It doesn't apply if you're just counting the number of gates and the size of gates in a single isolated circuit. So, analogous to studying running time, I might give you a circuit and ask you how big it is. Or I may give you a family of circuits and ask for the big O growth of that circuit as the number of inputs increases. In the next video, we'll build a fast adder called a carry look-ahead adder, and then use the techniques in this video to see how much bigger that adder is than the ripple carry adder.